In this video, I'm going to talk about electric field inside conductor. So what was it that conductor have and not the insulator have? What is the characteristic of electric conductor? It's free electrons, right? Free electrons, conductor have a free electrons. So here, remember the conductive material. Have free electrons. Electrons can move around inside a conductive material freely. So, if that means free electrons is a charge, right, inside a conductor that can move around. What if that's the case, if you have, let's say if electric field inside a conductor, what happens, right? If you have an electric field, if you have a, let's say, electric field, right? And then you put a conductor, you put a charge, let's say plus Q. This plus Q in the electric field that's generated by other charge. So then it's going to feel electric force. So whenever you charge, the charge in a, so here the explanation of this is charge in electric field fields have a force, electric force exerted. You know, by definition, remember, E is equals to force per charge. So we're going to have a force equals QE. So when you have a charge in electric field, you're going to have a force. So if you, let's say, because if you have a electric field inside a conductor, that means that all these free electrons in the conductor have a electric force to it. You're going to have a force, that means that electric force exerted electrons, free electrons. And they can move around. So for static state, which means that net force has to be 0, right? Then this FE has to be 0. You have to have an electric force to be 0. That means electric field is 0. You need to have a 0 electric field inside a conductor. Otherwise, you're going to have a force. For static, electrostatics means electrons are not in motion. Electrostatic means electrons are not in motion. You need to have electric field to be 0 inside conductor. So what's happening when you have charge let's say you have a conductive material, right? Charge move around. If you have a conductive material and then you have an electric field. So let's say I have an electric charge here, Q, and then this is conductor, metal. That's in electric. So this Q generates, has an electric field. And then if I bring a conductor, which has a free electrons in it, this may not be charged. This conductor is not charged itself, but if it's going to be in electric field that's generated by this Q, then these free electrons inside is going to arrange in a way to cancel electric field 0 inside this conductor. So charges arrange themselves so that electric field inside those free electrons, this means free electrons, right? So that electric field inside becomes 0. They have to go at the surface to make it inside is 0. So let's say, for example, let's say you have a metallic ball. So this is a metallic ball, sphere that has with plus Q charge. So it has plus Q here. That means that all the plus Qs, these plus Qs, to make it to be plus Q, they're going to be only at the surface. So that electric field lines has to be coming out these field line has to be perpendicular. And then it's only at the surface, right? Because imagine if you have this component, parallel component, that means that electrons can move around on the surface. So the only component, only electric field that the metal have for the electric field is going to be perpendicular to the surface. It has to be just here so that it cannot go anywhere. It has to be perpendicular. No parallel component. And then electric field is 0 inside. So charges only rest on the surface to make sure that electric field lines, in a way that electric field lines comes only perpendicular to the surface. When you have a shape like this, let's say conductive material with a conductive material again, and then this one also to have a charge. Still, even you have a charge, electric field inside has to be 0 because it's conductive. So how does these charge will arrange themselves? Again, they're going to be only on the surface. And then whenever you have this like a kinky point, like this not spherical, like not rounded, but like if you have a pointy spots, then they're going to be rather piling up here. So that, see over here, it can be like this, but you see how the electric field lines can be? It has to be always just perpendicular. Something like that. So when you have a pointy shape, like this pointy shape, charges tends to, for the conductive material again, only true with a conductive material where E equals 0, but charge tends to be coming in a pointy spot. So to have an electric field line coming out perpendicular. So again, electric field inside a conductive material is 0. So conductor, you feel like conductor attract electrons. Conductor attracts electrons, or conductor attracts those electricity, which is kind of true. Let's say if you have a cloud and then here you have a lightning rod, right? This is metal. That's pointy. So then when this charge is going to be built up, so let's see, here's the lightning rod, and you have a cloud, that rain cloud that's building up a charge. Remember we talked about interpolarization? So ground is typically slightly positive. Therefore, this rain cloud is going to be negative. Charge is going to be piled up in the bottom. The positive is going to be on the other side. So I mentioned the ground is typically positive, but let's say like a lightning rod, which is tall, long, and then at the end of the lightning rod is made pointy, and it's metal. Why? So that if you have these charges, they tend to accumulate more on the pointing edge. So it's easier that lightning tends to go to here, to the lightning rod, rather than a person here. So that's why lightning rod is made with the metal that's pointy on the top. Electric field inside the conductor is 0. Airplane get hit by lightning about, like in average, at least once a year. Those commercial airplanes get hit by lightning at least once a year. Every 1,000 flight hours, it gets hit by lightning typically. Airplane is made of old airplane. New one is made of like a different kind of a composite, like a graphene or something. But like a old airplane, typical airplane, you think about it's made of what type of material? Metal, right? So when the airplane get hit by lightning, airplane is made of metal. So therefore, electric field inside the airplane is 0. So as long as we make sure there's no gap in outside, the electric field inside the airplane is 0. I got hit by an airplane when I was in I got hit by a lightning. I never get right into the airplane. I got hit by when I was flying. I did have a time that lightning struck the airplane that I was in. You just hear a large sound, but nothing really happened because the inside the metal electric field is 0. So here you see picture See, a lot of airplane get struck by lightning. Here is, in fact, you're gonna see it. Oh, let me see. I should. I'm gonna show the sound too right now. So, okay.
You gotta run that. You gotta run that. You gotta run that. Jesus! Run that now. Run it now. Grab it and do whatever you have to do, GP. Tweet it. Tweet it. Tweet it. Tweet it. Okay. I'll just.
You see it around here?
Run it now. Grab. Jesus! Run that now. Run it now. Grab.
Maybe this is.
Oh my God! You gotta run that. You gotta run that. You gotta run that. Jesus!
Let me see. The sound comes after, so.
Oh my God! You gotta run that. You gotta run that. You gotta.
Maybe here. Sorry.
Oh my God! You gotta run that.
So like that. Here's another video. See, it keeps flying. It keeps flying. Another one. Keeps flying. Even after it got struck, see? So as you noticed that though, when airplane got struck by a lightning, the lightning hit the airplane that's typically comes from like one of the extremities. Like it could be the wing, it could be a nose, and then it gets passed through, the current passed through the surface of the airplane, and then it exits off from the another pointy part, like a tail or another wing tip and things like that. Makes sense, right? Because the charges, that's where the charges go. So that's what it is. And then yeah, those airplane that even not made of aluminum, they because for this kind of a lightning protection, they make sure to have like a very small grid, metal grid that's embedded everywhere around the airplane. And here is another demonstration. So let's see. What I have is a radio, and it's going to be turned into KCRW, Santa Monica radio station, 89.9 megahertz. Turn on the radio, KCRW, 89.9.
My stardust melody.
Metal. So I made this Faraday cage. People call it Faraday cage. It's made of metal, right? And I put the radio inside this metal. What happens to the radio? Cage, Faraday cage I made. So you see that I take out from the metal cage, it starts playing music again. And then this is one you get like some of those these days the car key has those talks to the car, right? That it's keyless or something that sends off the electric signal constantly. So what's those keyless or car? They keep the key is said keep sending electric signal to your car, and to avoid somebody stealing your car, people do sell little pocket Faraday box or something that's made of metal to put the keys in. So then if you kept inside there, they stop sending a signal that people cannot decode the signal coming out from your key. So this metal shielding is being used quite often. Let's say when you have a when you have a very sensitive stereo, and then if you want to get rid of the electromagnetic noise background, then you can wrap around in aluminum foil or something. Of course, it doesn't look good aesthetically, but you can do something like that to protect from the background noise. When I used to do an experiment, I make sure to cover in, for the sensitive equipment, I make sure to make metal shield so I don't get background noise. Inside there is the electric field is 0. So something like that. So when lightning is happening outside, you have 3 places you can go. Either stay in a car, or there's a house, but it doesn't seem like this house has any lightning rod, or there's a tall tree. Where is the place you want to be when there's a lightning happening? Right, you want to be staying in your car because your car is made of metal. And then inside the metal, electric field is 0. So you wouldn't feel anything as long as you have everything that's nicely shielded with the metal. And here's a Faraday. Nah, it's okay. So that's it for this video, and I'll see you in a class.